The engineer sees the car on the tracks. He hits the horn. He throws the train into emergency braking, and the train just keeps going. A fully loaded freight train at 55 miles per hour will travel roughly a mile and a half before it stops. The car is maybe 500 feet away. There is nothing else to do. The engineer knows exactly what is about to happen, and he cannot prevent it. Why? Why can't the train just stop? Doesn't it have brakes? It does have brakes. Powerful ones. Every single car in that train has its own brake system, its own set of brake shoes pressing against its own wheels. The locomotive has dynamic braking that turns its electric traction motors into generators to bleed off speed. There is nothing wrong with the hardware. People usually ask how heavy it is. A fully loaded freight train can weigh 6,000 to 20,000 tons, depending on what it is carrying and how many cars are in the consist. That is not a typo. 20,000 tons. For context, a fully loaded semi-truck maxes out around 40 tons, so the train outweighs it by a factor of 500. Weight alone does not explain the stopping distance. A heavy object with good brakes still stops. The real question is not how heavy the train is, it is how much grip those wheels have on the rail. And that number is smaller than almost anyone expects. Picture the wheel of a freight car. It is a solid steel disc, roughly 33 inches in diameter, weighing several hundred pounds. Now picture the rail it sits on. That rail has a slightly rounded crown on top. When the wheel meets the rail, the actual contact area between them, the patch where all the physics happens, is roughly the size of a dime. About 1 square centimeter. That is it. 1 square centimeter supporting tens of thousands of pounds of load. Now ask, why does this matter for braking? Because braking force is limited by friction. Friction is limited by that contact patch. You cannot generate more stopping force than the contact area, and the friction coefficient between those two surfaces will allow. For rubber tires on dry asphalt, the friction coefficient is typically between 0.7 and 0.8. That is why cars can stop hard. For steel wheels on steel rail under normal dry conditions, the number sits between 0.35 and 0.5 in laboratory tests. In real operation, engineers typically assume around 0.2 to be safe, because the rail surface is not a controlled environment. Rain drops it. Leaves drop it further. In autumn, when deciduous trees shed onto the tracks, the lignin in the leaves bonds to the rail surface and creates a coating with a friction coefficient close to that of ice, sometimes as low as 0.05. That is not a rounding error. That is effectively a lubricated surface under a steel wheel carrying 35,000 pounds. At high speed, the problem compounds. The French TGV, one of the most engineered passenger trains in the world, sees an available adhesion coefficient as low as 0.09 at 200 kilometers per hour. The physics of high-speed rolling is stripping grip from the system in real time. Locking the wheels up doesn't help. If the brakes seize the wheels completely and they start sliding instead of rolling, the friction coefficient drops even further because kinetic sliding friction is lower than rolling contact friction. The wheels start wearing flat. Flat spots on wheels cause violent impacts at every revolution, which can fracture the wheel and derail the train at speed. So the braking system cannot simply clamp down and hold. This is the same reason anti-lock brakes exist on cars. Maximum braking force comes from a wheel that is just on the edge of slipping, not from one that has already crossed into a slide. Trains have the same constraint, except they have far less grip to work with to begin with. Most people picture train brakes the way they picture car brakes. You push a pedal, a signal goes to each wheel, the brakes apply. Instantaneous, uniform, done. That is not how a freight train works. Freight train braking runs on compressed air. A single brake pipe runs the entire length of the train, car by car, connected by rubber hoses at each coupling. The locomotive's compressor charges this pipe to about 90 pounds per square inch. Every car has a triple valve connected to the pipe, and that valve monitors the pipe pressure. When the engineer initiates an emergency stop, the pipe pressure drops. Each triple valve senses the drop and triggers the brake cylinder on its car, pressing the brake shoes against the wheels. The system was invented by George Westinghouse in 1869, and, in its fundamental operation, has not changed since the 1930s. Here is the mechanical consequence of that design. The pressure signal does not travel instantly. It moves through the pipe as a pressure wave at roughly the speed of sound in air, about 920 feet per second. On a freight train that is 1 mile long, the last car does not even sense the brake signal until roughly 6 seconds after the engineer acts. 6 seconds at 55 miles per hour is 484 feet. The train has already traveled nearly the length of 2 football fields before the last car starts braking. But it gets more complicated. Once the pressure wave reaches a car, the brakes on that car still have to physically actuate. Air has to flow into the brake cylinder, compress against the piston, push the rod out, and drive the shoe against the wheel. The Federal Railroad Administration allows up to 10 seconds for a car to reach full braking pressure after it senses the signal. That means, on a 5,500-foot train, from the moment the engineer acts, it can take up to 16 seconds before the last car is braking at full force. During those 16 seconds, the front cars are slowing hard. The rear cars are still coasting. The train is behaving like a slow-motion collision happening inside itself. The front decelerating while thousands of tons of cars behind it continue pushing forward. The couplers between cars compress and then slam, sometimes violently. Engineers call this slack action. In extreme cases, it can derail cars in the middle of the train. This is why, when a freight engineer sees a problem, the first instinct is not always to slam the brakes into emergency. A controlled service brake application, done early, gives the pressure wave time to travel properly, gives the slack time to equalize, and keeps the train from folding on itself. Here is a specific scenario that railroad safety investigators work with regularly. A freight train is moving at 29 miles per hour, which is 42.5 feet per second. The engineer spots a vehicle on a grade crossing 485 feet ahead. Average human reaction time is about 1.5 seconds. In that 1.5 seconds, the train travels 64 feet. The engineer has 421 feet of distance left in which to slow the train. At 29 miles per hour, even with full emergency braking applied immediately and perfectly, a freight train needs far more than 421 feet to stop. The calculation requires accounting for reaction time, brake propagation delay down the consist, individual car actuation time, the weight of the train, the friction available from the track surface, and the grade of the track. Running those numbers, the train arrives at the crossing, still moving. Maybe slower, but still moving. This is not hypothetical. This scenario plays out thousands of times a year at grade crossings across the United States. The Federal Railroad Administration records more than 2,000 grade crossing incidents annually. Engineers who survive these events often describe knowing the outcome before it happens. The horn, the brake handle, the physics doing exactly what physics does. The question that gets raised every time is, why did the engineer not see it sooner? The answer is that even if they had, the distance required to stop a freight train at operating speed is measured in miles, not feet. Sight lines at rural grade crossings are often blocked by vegetation, curves, or changes in grade. In many cases, the train would need to have been braking long before the obstacle was even visible to stop in time. Trains are not designed to stop on a dime. They were never meant to be. The entire economic logic of freight rail depends on the fact that steel wheels on steel rail have almost no rolling resistance. A freight train can move 1 ton of cargo 480 miles on a single gallon of fuel. That efficiency comes directly from the same low-friction contact that makes stopping so difficult. The design is a deliberate trade-off. The signaling system that governs train movement was built around these stopping distances. Block signals, which divide the track into sections, are spaced so that a train traveling at its authorized speed has enough distance to stop before reaching the next signal if it shows danger. The system does not assume trains can stop quickly. It assumes they cannot, and it adds distance to compensate. Positive train control is a GPS and radio-based system. Congress mandated after a 2008 collision in Chatsworth, California, that killed 25 people. PTC knows where every train on a given line is, what speed it is traveling, and what track authority it has. If a train is approaching a signal it should not pass, or is closing on another train in its block, PTC can automatically apply the brakes before the engineer acts. It does not make trains stop faster. It gives the stopping process more time to begin. But PTC has a significant limitation that rarely gets mentioned in coverage of rail safety. It is designed to prevent conflicts between trains and to enforce speed limits. It is not designed to detect obstacles on the track. A car stalled at a grade crossing, a rock slide, a piece of equipment dropped from an overpass, a person on the tracks. None of these are visible to PTC unless the railroad has installed specific sensors at that location. The system knows where trains are. It does not know what else might be in their path. Every time you wait at a grade crossing, watching a freight train roll by at speed, you are watching a vehicle that committed to its stopping distance several minutes ago. The engineer did not decide to pass your crossing just now. The train's trajectory was set long before it came into view. The design that makes rail freight the most efficient land-based cargo transportation system in the world is inseparable from the design that makes stopping so hard. Low friction, low rolling resistance, massive momentum. You cannot keep one without accepting the other. What is changing is not the physics. It is the awareness window. Better sensors at crossings, improved communication between infrastructure and trains, and more sophisticated automation. The goal is not to make trains stop faster, because that may never be possible within the constraints of steel on steel at scale. The goal is to start the process earlier, to extend the moment between knowing something is wrong and arriving at it. A freight engineer who has been in the cab for 20 years will tell you, the horn is not for the obstacle. By the time you are sounding the horn, the math has already run. The horn is a warning to anyone nearby who might still move. The train stopped being stoppable well before that moment. That is the honest answer to why trains do not just break.